Okay. So we are talking about electric potentials, right? So, okay, what is electric potential exactly? So, the electric potential is the work done by an external force in bringing a unit plus positive charge from a point R to point P. So, like visually, if you want to see it, so let's say your charge was initially at this point. So, call it R, okay? And there is some kind of external force, okay? Some kind of external force which is acting on the charge Q and which is bringing the charge from point R to point P, okay? So, and what I mean, the amount of work done uh, per unit charge is what we call as our potential, okay? So the potential is always a relative quantity, so you always measure with respect to some point, okay? Basically sometimes most likely you try to measure it with some point where the potential is zero. Then sometimes you measure the potential with respect to infinity, okay? So we'll go on to that later. Okay, so there are, okay, so first of all what I am doing here is I am giving you a gist of what kind of formulas or what kind of concepts that we'll be needing, okay? So the gist is very concise, okay? And if you don't understand them for the first time, so don't worry, okay? Because we'll work out some of the problems and that will clear out most of your doubts, okay? Okay, so for the next one, okay, so what I have here is, so this is a snippet from your NCRT book, okay? So what I have is some point charges, okay? So like Q1, Q2, Q3, Q4 and some Q, okay? So the work done on a test charge Q, okay, by the electrostatic field due to any given charge configuration is independent of the path and depends only on the initial and final positions. So that means that let's say we have this charge Q, okay, and our sole task is to take this charge Q from point P to point R. You can take any paths, right? You can take any paths. You can go through like, okay, so you are bringing from R to point P, that's fine. So you can take any path like this, the straight line, or you can take a curvy path, okay, or you can take something more funny kind of paths, okay? But it doesn't matter what kind of path you choose. Someone is joining, yeah, let me admit him. Okay, yeah, okay, so hi Shudhanshu, we are just starting, okay? So yeah, if you have at any point you have any question, just ask me, okay? So the point is, if you are bringing any charge from one point to other point, the work done doesn't depend on whichever path you choose, right? That is a very important and very specific property to these electric fields, okay? So like you could have chosen any of these given paths to bring the charge from point R to point Q, okay? But none of them would give you any different results, okay, because they all truncate or they all finish into P and R, okay? So why this is, so this is something called the property of this electric field. So electric field is a conservative field. So for conservative fields, the work done the work done doesn't depend on the path, right? It only depends on the terminal points, for instance here R and P, okay? So we'll see some examples of this thing later on, okay? So the other important thing is, now let's say you want to calculate one this potential, electric potential, given some charge configuration, okay? So from the previous chapter, I think it was this Coulomb's law chapter and the electric field chapter, you already know the electric field's expression for some given configuration, right? You know for a given, for a point charge, that is just like 1 by 4 pi epsilon 0 times Q by R square, okay? You know for some other things, some rods, you know for circles, you know for some circular discs, okay? So from that chapter you bring on all of the information of this electric field, okay? And what we have to do is we will have to just take a dot product of the electric field and we will have to take a line element, okay, from the path between A and B. So like I said, if there is some point A and there is some point B, you could have chosen any path, okay? So it doesn't matter. So this dl is nothing but the smallest part of this AB, okay, the infinitesimal part of this thing. So dl has some direction, okay. So dl, generally speaking, you can write this dl like dx I cap plus dy j cap, okay, something like this. And you will have to take a dot product with the electric field that you already obtained from the last previous chapter, okay. Okay, so now if you do this integration, okay, if you do this integration and you take the limit from a to b, you will get the potential difference between those 2 points, okay. So just make this point very clear. Let me repeat it again. So to calculate the potential difference between 2 points, we will have to calculate this integration, where the limits of this integration is given by these 2 points, okay. We'll look into this in much detail when we will do some problems for this thing, okay. So there is another important thing that you will see that in books they don't all the time, they don't mention 2 points A and B. They only write the potential as a function of r, as a function of position. So why is that? So that is like, as I mentioned before, the potential, you will always have to measure the potential with respect to some point, okay. So here mostly in the books what they do is they assume that the potential at infinity is 0, and with respect to that 0 they measure all of the potential difference. So when you write V as a function of r, that means that you are bringing some unit charge from infinity to some distance r, okay, and you just calculate the work down in between, okay, that is your E dot dl, and there is also this minus sign, okay. So this is the basic recipe to calculate the potential, okay, for any kind of system, okay. So let's look at some examples, some very basic examples of how this potential is calculated. So like for example, let's say I have a point charge here, okay. So the point charge has q charge, okay, and it is just a point. So we know that from Coulomb's law, we know that its electric field is just 1 by 4 pi epsilon 0 times q by r square, okay. So this is just the electric field. Now if I want to calculate the potential at some point r, what I will have to do is I will have to do this integration. The integration here will be e to d, E dot dl, and we will be integrating from infinity to r, okay. So here also we will assume that at infinity, whenever this r will be infinity, then this v will be 0. So this is our basic assumption, and with respect to that infinite, r is equal to infinity, we will measure our potential, okay. So what you can do right now is you can just integrate. Now see the how I have written the dl here. So you see, so if there is some point r here, and you are bringing the q which was sitting at infinity, right, and let's say you are bringing it in some paths, right, but as I mentioned, for this electrostatics problem the path doesn't matter. So what I will do is I will basically bring it along this line, right. I will not make any funny business around these paths. So I will bring it along a line. So if I bring it along a line, if there is a circular symmetry, so this dl, right, so that the dl which I was writing before, dl is nothing but dr cap, right, it is nothing but dr cap. So yeah, it is nothing, just dr cap, okay. So what is dr cap? Dr cap is r cap times dr, right. R cap is the unit radial direction times the dr, okay. So what I will do here is I will just plug in everything that I know about the point charge, namely this electric field, and I have already written this dr here, and I think you must remember that there is r hat in this Coulomb's law in this electric field, and also there was an r hat coming from this dl part, right. So r dot and r dot both are unit vectors, right, so they give you 1. So here I have not bothered writing this r dot, okay. So now we will have to do this integration, right. So if you see, so there are many terms, but the integration is really simple, right. So the integration is something like dr by r square, okay. You can just replace this r by x, dx by x square, and you know that the integration of this thing, right. So integration will give you just 1 by r, and you plug in the limits and you will see that you will get just 1 by 4 pi epsilon 0 q by r. Okay. Now this very innocent looking result, this consists the building block for calculating the potential of extended objects, right? So like we have calculated for a single point charge here, the potential for a single point charge. Now we'll be using this formula later on to calculate the potential for some extended object, okay, that will not be a point charge anymore, and we will see how to do this. Okay. So let's move on to the next thing that I want to tell you about. Okay, so till now, do you have any questions, or you are all good? Can you just follow these things, or if you don't follow, just let me know. Okay, because I think Pratik was taking your last class. He probably did some other chapter. He didn't probably do this this electric field chapter. So have your class teacher covered the electric field chapter in your class? Can anybody tell me?
Yes, sir.
Okay. So can you follow this? Can you follow this potential calculation? I mean, what I am doing here. I mean, this is simple, right? You can follow it.
Yes, sir.
Okay. Okay. Yeah. Okay. So let me show you how to calculate the potential for a dipole. Okay. So just to remind you what a dipole is, it is just two opposite charges, right, which is separated by a very small distance, right? So for dipole, the exact definition is the q that we are writing here goes to infinity. Okay, so the charges are huge, they are almost infinite, but the distance that is given for the dipole is very small, it is almost like you cannot distinguish them. Okay, but the limits, if you take the proper limits, then for the dipole moment, which is given by q times d, and I have taken those two limits, right, q tends to infinity and d tends to 0. Now if you take the properly the limits, you will see that even the q goes to infinity and d goes to 0, this dipole moment will be finite. So this is the precise definition of a dipole. Okay, now so for a dipole, like we can calculate, let's calculate the potential at some point p. Okay, here, so I want to calculate the potential at here with respect to some point where the potential is 0. Okay, so here you see that there are two charges, right, 2 point charges. So I will write the potential for the positive charge first, so which is given by 1 by 4 pi epsilon 0 q by r1. Okay, so r1 is this distance, so this whole distance is r1. Okay, and the other part is that there is this minus q charge, and the distance from this point p is just r2. So then I will write minus q by r2. Okay, so now the task is to find the r1 and r2. Okay, so we know that this distance, the separation between the dipoles is given by 2a. Okay, and this distance from the dipole center to the point p is given by this bold r. Okay, this r. Okay, now from this information, okay, and there is also this angle theta. So from this information, what we would like to do is we would like to calculate these distances r1 and r2. Now in that regard, so this triangle will help us out. Okay, so now if we have this kind of triangle where the arms are given by a, b and c, and the angles are given by these three Greek letters alpha, beta and gamma. So in this triangle, let's say I am asking you to find the length of this a given this b, c and alpha. Okay, now how to do that? Now the straightforward way, I think you all know this from your maths class probably. So this is a square is given by the opposite arms to the a, the adjacent opposite arms to the a. So we will just do b square plus c square. Okay, so b and c were opposite to a, and then we will take a minus, we will do a 2 times b and c. So this b and c are all again, they are just adjacent arms, adjacent edges, and we will write the cosine of the angle that is between this b and c arm. Okay, so you see the pattern. So like if you are asked to calculate this b square or the b, then similarly you will do the opposite adjacent arms. You will just square them and add them up. So here it will be a square plus c square, and then you will do minus 2ac, right? 2a and c, which was opposite to b, and you will write the cosine of the angle which was opposite to the b. Okay, so everything opposite to the given arm. So for again c square, you can do this in your mind. So for the c square, what we will have is the opposite arms are a, b. So that's why there is a square plus b square, and we will have to take the cosine of this gamma, right? Cos gamma. So there will be a minus, and also multiplication of ab, right? So simple, right? So we'll try to use this thing to calculate our r1 and r2. Okay, so similarly, so for the r1, so how do you calculate the r1? So for the r1, you see this is the r1 sitting here. So the two opposite arms are given by so this is one adjacent arm, right? So this is given by length a, only this part. Okay, and this arm is given by r, right? So how do we write this? So we'll write for r1 square is equal to a square is this part, plus r square is the magnitude square of this distance. Okay, plus, okay, not plus, so it will be minus 2a times r, and there will be cosine of the opposite angle, which is given by the theta here, right? So 2ar cosine of theta. So now you know the r1 square. Now to calculate the r1, you will have to just take a square root, right? But so here so there is some scope of approximation. Okay, so because as I mentioned, the dipoles are actually their length is very small. So the distance between them, this d is tending to 0. Okay, the distance is very small, and the r, the distance we are measuring the electric potential at, is very large with respect to their separation, right? Now if this is the case, the a by r whole square can be neglected, so because that will be even smaller, right? A is smaller and r is large, right? So that will, and you will take a square of it, then it will make it even more smaller. So and you can just ignore this factor, right? So this is some approximation that all the books do. So what we are doing right now is we are just neglecting this term, right? And the rest of the term here is 2ar by cos theta. Okay, and we can take a square root. So this sign means we are approximating. Okay, so r1 is given by r plus r times 1 minus 2a by r cos theta to the power half. Yeah, this is the square root. But we don't need r1, right? We need 1 by r1. Okay, so what we will do next? So we will write 1 by r1. So here the r will come in the denominator, and the half will become minus half. So you see what I will do now is I will do a binomial decomposition, binomial, right? And I will just take the first factor. So first factor will be so there was minus half. So minus half times minus 2, that will give you plus 1. So that's why I have plus 1 here. And all of the other next terms in this binomial expansion will be like a by r whole square, right? And next orders a by r whole cube. But we already neglected all of them, right? So we will not take any of those. So as I have calculated this r1, similarly you could have calculated this 1 by r2 in a similar fashion. So the only thing that you will have to check here is, like, so this was the theta, but this is not the theta. This is pi minus theta. So in the cos's argument, you will put pi minus theta. So then you will get a plus sign here, and you can follow, right? So what I will do next is I have contributions from both these dipoles, and I will just add them up. I will just plug them in the formula, right, as it was before. So this is given by 2a by r square cos theta, right? So 2aq, you can recognize this is just the dipole moment. So this is the distance between the dipoles, and this is the charge of the dipoles. So this is the dipole moment. There is r square, right? And there is cos theta. So what we can do is we can actually write this in a vectorial notation, where we will just take a dot product between p and r cap. So p and r cap, this dot product will also give you cos theta. So here I'll ask you to remember this fact that when you calculated the potential for this point particle, it was going like 1 by r, right? So the v was going like 1 by r, right, for the point particle. But when we calculate it for this dipole, we see that the v here is going like 1 by r square, right? Strange, right? So, but we will see that this is not so much strange. For any point particle, you will always have 1 by r. But if you will go beyond point particles, you might have different kind of powers. You kind sometimes have log functions, some very bizarre functions, right? So, yeah, this kind of thing might happen. So the next, okay, so the next thing about the potential is a scalar quantity, right? So scalar means it has only a value and it doesn't have any directions, right? So you don't have to think about any components at all. So what you have to do is, if you have some bunch of charges here, q1, some q1, q2, q3, q4, q5, and I am asking you to calculate the potential at point P due to this all of these charges, right? So how do you calculate this? So you just sum it up, right? You have to sum all of these potentials, okay? So how I have written it here is, so I want to calculate the potential at point P, okay? Now how to do that? So for that I'll calculate the potential between the point 1 and point P, right? So then I'll move on and I'll calculate the potential between point 2 and point P, then point 3 and point P, then point N and point P. So basically you will have to calculate the distance, all of these distances, right? And you will just plug in and you will just sum it up. You'll just sum to get the whole potential, okay? And so here I am mentioning this for a system of point charges, right? But it doesn't have to be like that. It can be something complicated, okay? It doesn't have to be point charges, okay? Now let's see if you have some extended objects, right? So how I have drawn here 1, 2 and 3. They are some extended objects, right? So their potential does not go like 1 by r or 1 by r square. They go somewhat differently. They go like some log function or some other function, okay? Now if you want to calculate the potential at some point P, then you will just plug in the potentials that you already have calculated before for all of these three objects separately, right? And you will add them up at point P, and that will give you the resultant potential at this point P, okay? So yeah, these potentials are very easy to work with rather than the electric fields, okay, because they are just scalars, they are numbers, okay? Okay, so there is this also important concept. This is very important. So this is the equipotential surface, okay? So like the name suggests, so this is nothing but the surface with a constant potential, right? Constant potential. So like for example, if you have a point charge like I have here plus q, then if you just draw some circles, concentric spheres, okay, then on the all of the points of the spheres the potential will be same. So like for example, let's say v on this outer sphere is given by 10, okay? So this is an equipotential surface. So on all of the points the electric potential is same on this surface, okay? Now if you go inside, the potential might change, okay? So let's say for this sphere we have v is equal to 5, something like that, okay? Just to give you an idea. So you can see that here also the potentials are denoted, the same potential is denoted by some surface, okay? So here it is just a sphere, okay? So this is the whole idea about the equipotential, okay? So another very important fact is the electric field is always normal to the equipotential surface, okay? So like if you have some equipotential and if you want to draw some electric fields, then you will just have to calculate the normals of these surfaces, okay? And you will just join them. So they are always normal, okay? So like here I have tried to draw this, but this is not a very good drawing. So the blue curves are the equipotential surfaces, right? and these arrows, the red arrows, these are the electric fields that is emerging from this point, okay, from the origin. Okay, so this is how you think about electric fields and equipotential surfaces. They always are perpendicular, so all these angles are always perpendicular, and whenever they touch, they always are perpendicular to each other, right? Okay, so with that, let's do a few simpler problems. Okay, uh, so okay, so can you just tell me that how long is your class? Is it up to 10 past 1? Is it up to 1:10 or is it up to 1?
110.
Yeah.
110.
So I have 10 minutes of time. So yeah, let's do few problems. Okay. Okay. So let's read along the problem. When an electron moves from A to B along an electric field line in this figure, the electric field does some work, does 3.94 into 10 to the power 19, 10 to the minus 19 joules of work. What are the electric potential differences VB minus VA, VC minus VA, and VC minus VB? Okay. So okay, what they are asking is they are saying, okay, there is some electron which was sitting at point A, right? Point A to B, yeah. So which was here before, okay? And so there is some work done on this electric field to bring it back to this point B, okay? And the net work done to do this work is given by this, okay? This 3.94 10 to the minus 19 joule, okay? So now they are asking to calculate the potential difference between VB and VA, okay? So now I also look at these lines also. You see, so they have denoted these orange lines as the equipotentials, right? So that means that potential on all of the points, on all points of these surfaces are same. So potential of all on this surface are same, but so this is some other potential and this is some other potential. Let's call it V1 and V2. Okay. So so they have mentioned that how much work they have done. Okay. So how I define the potential is the work done per unit charge, per positive unit charge, right? So the work done is given by this right. So I will just plug in the number and we will divide with the Q. Okay, so because the potential is given by the work done per unit charge. Okay, so okay, so you just plug these numbers in your calculator and you can just calculate it, right? The number is not that interesting, but the concepts are interesting. Okay, now, okay, so this is done. So now the second question is to calculate the potential difference between point C and point A. So from between here and here. So how to calculate it? So we don't need to do any extra work, you see. So because we already know the potential difference between VB and VA, and you see that this B and C, they are also lying on the same equipotential, right? So that means the potential difference between B and C are same, so there is no potential difference. So this difference is same as potential difference VB minus VA, right? But we already know what is the potential difference is, right? So then the answer is the same as the last one. Okay. So also, so the last part is what is the potential between this VC and VB? So potential difference is nothing but the potential between here and here, and you just subtract it. But you just notice that there is no potential difference between B and this B and C, right? Because this B and C, they are lying on the same equipotential, right? So this is just 0. Okay.